I'm happy to share some of my experience in this field with you, coming from academy, industry, corporate, startups. So I've worked on healthcare and on other computer vision, machine learning, deep learning applications, and I'm happy to share the story and the experience. So the question is, will the introduction of AI revolutionize medicine and healthcare? The question is, I think it will, but the question is when, and also what does it take in order to do this transformation and revolution? Because obviously we've been working on this for a long time, and we are still not there, okay? And of course, we've all been, I guess, familiar and amazed by the many breakthroughs that AI has been showing us in the last couple of years. I currently work in Mobileye. So in Mobileye, we develop self-driving cars. This is one of the amazing, I think, technologies that I hope we will all be fortunate to enjoy very soon. And so this is one example. Another example is GPT-3. I guess you've all seen or heard about it. It's the technology that came out from OpenAI that actually produces human-like text. And it produces human-like text in such good quality that it's very difficult to distinguish between the text that comes out of the transformers and the machine and the deep learning application compared to human text, okay? And the next step after GPT-3 was DALL-E that also came out from OpenAI, and you can see here nice examples of actually images generated based on text. So you can imagine what you'd like to see. For example, you want to design an armchair in the shape of an avocado. And here are the images that come out of the algorithm. And obviously, it has never seen such images before. And this is like if you type DALL-E or type GPT-3, it's available to each one of us to work with and see these amazing effects. And the question is, will we see such things in healthcare too? And it's important, I think, to note that Mobileye and also, I guess, Tesla reports that they've been training on billions of miles of data, okay? And same for GPT-3, okay? You can see here the report from the paper, I guess, of the number of tokens that the algorithm was trained on. We're talking about billions of data, and I don't know who of you are working today in healthcare and training algorithms, but we usually do not train on billions of data, okay? And maybe this is one of the things that we need to keep in mind, that in order to get there, we need to have such amount of data to train on. But still, healthcare also has blossomed, and of course there are significant breakthroughs in healthcare too. And this is just from a paper coming out from 2021 from the American College of Radiology. So these are some of the FDA-approved products that you can see already out there, and you have them in different modalities, in different applications, for different regions of the body. And of course, this is only radiology. In healthcare, you'll have many more. And the page of the FDA is getting longer and longer with approved products. Coming from Zebra, that was my last my recent healthcare experience. We approved 10 FDA, we have 10 different FDA approved products. And they really range in different domains and different types of modalities and different applications. So we have a product we had a product for bone health solution, cardiac solution, neuro solution, okay, identifying intracranial hemorrhage and CTs, chest solutions, identifying different diseases in chest X-ray, which is a different modality, of course, an orthopedic solution, which has generated 3D reconstructions of bones based on 2D X-rays and allows to do actually surgeries without being without putting the patient into a CT or into an MRI, which can sometimes be expensive and not accessible, and a mammographic breast cancer solution. Okay, and I'll speak about them as we go along in the context. And of course, in Israel, we also have many startups ranging in multiple domains as well. So there is activity in the industry, which is very significant. And of course, in the academia. So I think the most significant breakthroughs in publications in healthcare came in deep learning, started in 2016 with the Google paper of diabetic retinopathy. And I think there are important conclusions to take out of that paper. And we progressed since 2016 with the dermatology paper by Stanford in 2017, radiology papers, chest x-ray, breast cancer, CT hemorrhage. Many papers have been coming out, and as you will see, the amount of data in all these papers and publications is very significant. And of course, the motivation is clear, okay? We have a number of studies and procedures steadily increasing. The number of radiologists and healthcare practitioners and clinicians are insufficient in many areas of the world, and this process is error-prone, and we would like to support it as much as we can in order to improve healthcare. The question is, can AI transform healthcare as it does in other domains, okay? Because the progress in healthcare is slower for some reason. And still we have many AI applications across all the health span. We have applications for embryo selections. We have applications that follow up for mental health, for death prediction in hospitals. So we really have a lot to do. And we also have a lot of information, okay? So you can really build a virtual medical assistant with all the information that you gather on a human, whether it's social, behavioral, environmental, and of course genomic and other many biological inputs that we can take that we can follow through. However, it is clear that healthcare has many challenges. I think that there are some challenges that are very unique to healthcare. So one of the first one is the low prevalence of some of the diseases. You can have very unique types of subtypes of diseases, and you would be required to support them. Okay, building a breast cancer application, you can't, and wanting to assist and predict, you cannot skip some of the categories. Okay. Additionally, you have subtle, fine-grained categories to look into. Look at these two images. So my colleagues working on computer vision, looking at horses, faces, cars, when I was training for my PhD, and finding myself looking at really, really tiny findings and the percentage that they take out of the image is very small, okay? And so it means that the task is in a way more difficult and requires significant expertise. Additionally, there are many acquisition artifacts in these types of images. Of course, that are related to the physics in which we acquire images. The resolution and the size of the data can be significantly larger, okay, compared to having a 2D little image, having a full 3D volume that maybe has some motion in it, so you acquire it over time. It's a significant amount of data that you have to take into account. There are variations between machines and between protocols, and one of the most important thing in healthcare is the intra and intervariability between the radiologists. Okay, so when we're driving in our car, and most of us will see the red light, we'll see the stopping sign, we'll understand the OCR that is on the road properly, and the same. Still, a radiologist usually tend not to agree, and you can really look, and it really makes categorize the different tasks and applications you want to take into account and you want to find a solution for, you should really look into the agreement that radiologists have or radiologists or clinicians have when they come to look into this problem. Additionally, there are explainability issues, which we have in all through AI, and we have generalization issues and real-world issues, which are also we have all through AI. And specifically in healthcare, I think it's a multimodal problem. We will see in the examples later on that the clinician has a huge amount of knowledge when it comes to solve a problem. He knows the anatomy. He knows the information about the physics of the acquisition. He knows the history. He knows he has blood tests. He can have clinical data. He can have textual data. He can have imagery data. And all of this information is important in order, if you want to build a machine that is able to act and solve the problem as good as the human, or at least support him in a valuable way. We really usually don't say that we want to replace humans, but we want to support this process and make it more efficient and improved in a way. And of course, there are privacy and security issues, which are very important, and regulations. Okay, so we have to meet regulation FDA processes when we work in healthcare. And just as a small example, okay, what the effect of machine learning or deep learning can bring. So this is something that I took from a medical resident, and he's actually working in deep learning, but also practicing clinical application. And what he says is that when you look at really the most naive visualization and explainability algorithms for algorithms, you can see here that the machine, what I'm presenting is the sort of heat map that has positive values with green and yellow shading here for positive predictions. And you can see that actually it finds the enlarged heart. The heart shouldn't be so large in an X-ray, okay? Still, it's downweighted here in negative values, the areas that are in purplish, the fact that the scanner is not a portable scanner. Now, for whoever is practicing medicine, you know that the patients that are very sick, they will be lying down. They won't be, because they're too sick to stand up, and there will be a portable machine doing their X-ray for them. And actually, what we see here is that the algorithm, the deep learning machine, is pretty lazy, and instead of looking at the heart, it's actually looking to see if there's a portable sign of a scanner here, which there isn't. So it downweights the score that it gives this cardiomegaly finding, okay? So this is just an example that we have an issue with taking these algorithms, training them, and not being sure about what they do, okay? And explainability in healthcare is important in all algorithmic domains, but it's really important in healthcare in order to verify the weaknesses of the algorithm. It has many legal aspects to it, and there are obstacles when you bring it to clinical practice and you want to work with clinicians and you want to gain their trust. It actually, I think, matters more. And another thing coming from the same resident, which I really appreciate sometimes to read his comments and blogs, this was the reaction that came out in 2017 when Stanford released their chest X-ray algorithm, claiming that it reaches a human performance. And that is why I think in one of the important takeaways from this talk is that we really need to be careful when we validate, and we really need to be careful on what we claim. Because what he was saying is that actually this experiment was not validated. The Stanford study coming out, which was later a Nature paper also, did not include prior information as radiologists do have, did not provide the radiologist the lateral view that it does have, did not have The data set was too small. The clinical data and the labeling that was performed there on the reports was a mess. And it did not work. They did not allow the radiologists that were competing against the algorithm to actually do their routine workflow. And I think it's very important when you do comparison and when you provide validation to really do an apple-to-apple comparison and be very careful with your claims. This is, of course, something coming out in 2017. A lot of water has passed under the bridge since then, but still I think it's true. And this is why I think that when we build algorithms for a real-world scenario, validation is very important. Validation, when I work with students, when I work with my teams, I usually emphasize on that we have to really compare ourselves to the prior set of the art, so prior publications, prior work obtained from other companies. We need to compare ourselves properly to humans. We need to compare ourselves, we need to have sets that can be regulated for the FDA, which is also a different standard with different requirements. And we also need to do in the wild comparison, which is essential, okay? And in the wild comparison means that when you have an FDA set, you'll usually have it positively enriched. You'll have more samples that represent some unique finding that can be very rare because you have to prove that you are able to work on it. But eventually in the field, the data flow and the patients that come in can be slightly different. And additionally, you have to have and additionally, you have to embed your system into the clinical workflow. And I will demonstrate how important these ideas are. So this is like, I would say, another idea that I think we should all keep in mind. And now, as we talked about the multimodality part of this game and this challenge, of course, and if we want to have huge amounts of data, we cannot annotate them. It's not feasible, it's not cost effective. Some companies can annotate more, but we just can't do it. And one of the ways that we overcame this at Zebra, which is now Nanox, we built a really strong NLP type of line of work, which allows us to work on the reports coming out from radiologists. So you can see here a typical report. A report usually has 3 parts. It has the finding section, the impression section, and an additional other section. And you need to really go over with your algorithm on all these parts and extract the labeling for this finding. You can also use, of course, EMR, and you have the different types of images that you have for this problem, whatever problem you're working on. And these sort of labels are called the silver standard labels. And you need to keep in mind that they are very noisy. So, for example, this is an example from a COVID project that I once was involved in. You can see the text that the radiologist would write, dense opacity, more infectious than mass-like. What do you do with these sort of sentences? They're usually very, they put in a lot of borderline, questionable, undetermined phrases that you really don't know what to do with them. And you really need to keep in mind that when you provide a prediction based on NLP, it's pretty noisy. Still, we found it very efficient, and it's important for scaling up, and it's also important because really the NLP technology has gone such a significant way in other domains, and we should make use of it in healthcare too. So you have the personal assistants, the autocomplete, the GPT-3, as we said, and all of these are very, very useful and starting to support healthcare as well. So being able to take the reports and analyze them with algorithms, you can start solving problems like chest X-ray. Chest X-ray is just an example for a multi-finding problem where you see the different types of finding. I'm not sure, it takes a very long time to even think that you you may identify some of these findings. It's a very admired expertise that when I work with radiologists and look into the work, it's very hard to differentiate. And of course, you have millions of images, multiple data sources, okay, coming from institutions spread around the world, multiple manufacturers, and multiple modalities and views, okay? And all of this needs to be taken into account. The process that is really in practice today, and there are many companies and also good publications, they started with taking the reports and doing a rule-based labeler. When they separate the sentences in the report to blank, uncertain, positive, and negative, and provide these labels to the images, and train algorithms in such a way on millions and millions of chest X-rays, and being able, in some of the cases, to obtain very good results. Now, the thing is that it's a two-way road, right? Because you can train, in a way, you can train your images on text, you can train your text on labels coming from the images, and actually the smartest thing to do that is being done today is to do this jointly, okay? Take both, take them together into one space and train them together and it has been shown to get better results. And you can do that in chest X-ray, and you can do that in head CT. Head CT is more difficult in a way because you have a patient coming in. It has multiple, one study can have multiple protocols, okay? So you have contrast, non-contrast. You can have several types of images for the head at the same day, and you want to find the specific location of a brain bleed or a stroke. And the report will give you some high level, it usually will give you some high level information of where it is located. But taking this weak label, okay, and just to make sure everyone is clear, it's clear to everyone, when you have a really full supervised location of the finding, it's one level of annotation and work to annotate such data. Taking the report, which is a high level, and it provides for all the volume together and all the different volumes that were acquired on the same study, a summary it's a more difficult task, but still it's feasible, and actually we have done it and others too, and with a huge amount of data you can get really nice results, and to get it effectively to work in the clinic, and actually there are already products like this around the world. So we have many modalities, and actually these modalities can also be applied preclinically. I really encourage people not to hesitate to do these experiments when you have something that you want to test preclinically. There's all the imaging available for small animals, and this technology is actually not yet being applied and developed for small animals, and actually this could be very, very useful. And so the process, I think, has been like developing in healthcare the imagery, the type of modalities that we use today. If it's optical imaging, if it's MRI, if it's a CT, if it's X-ray. Then we had all the formulation of digitization and the DICOM format that makes it available throughout all the different places of the world. We have a sort of standard that we can speak to. And then today, this is taken from another Stanford paper. You have these deep learning approaches that are starting to find, for example, bone fractures automatically. So we have we're actually walking throughout this way, and hopefully we will get there. This is a nice story, I think, of the Google journey in this field, where Google, as I said in one of the first slides, developed the diabetic retinopathy approach, which was one of in 2016. It was a paper that came out by Gulshan et al., and it was supposed to categorize, as you can see, very high level, these 5 different categories. And they had very good results at the time, so 97% sensitivity at a 93 specificity was considered very good. They had a huge data set, as Google usually has, okay, 100K images. This is the level of research and the amount of data that you want to work on when you're trying to solve a problem. Still, Google is struggling to get this to work in practice, and there are papers coming out describing their difficulty in making this to work in Thailand, for example. And the question is why? Why, if you have such a good publication, I think they had 54 US clinicians annotating this data and grading each image 3 to 7 times, still, and no startup and very few companies can build such a machinery, okay? They had a team of 20 researchers, huge amount of data, huge amount of annotators. Still, their product from 2016 is still struggling to get into the market. And the question is why? So I think that we can skip this. I think there are a few reasons for it, and it's interesting to keep that in mind when you are, of course, when you're doing working on a publication or working on a research, your goals should be one, and when you're working on a product and trying to get it into market, I think your goals should be different. And here, the thing is that they did a few things, and it's actually a good practice. Okay, they took the consistent taggers. There were taggers that were inconsistent. These inconsistencies taggers that you're going to throw out when tagging your data, you're going to meet them back in Thailand in the field, okay? And then you'll need to know what to do with them, okay? And how to compare your results with them. They had acquisition parameters that were very standardized, okay? It's not like that when you go to the real world. The real world will have different protocols, different training, different lighting condition, and all of this is waiting for you out in the field, okay? Additionally, they had socio-environmental factors that affected the model performance. So they had a nurse workflow that they were not familiar with, and they had to adapt to. So the conclusions actually that come out in their journey, and when they document their conclusions, is that first of all you have to have prospective studies versus only retrospective studies, which we usually do in the academia and also sometimes in startups, and to use authentic patient data and really work in the field with your product in multiple regions of the world as much as you can in order to see that it's clinically effective. Okay, so another type of application is breast cancer, which I think, in a way, the technological story is more optimistic, in my opinion, for this domain. So, of course, the statistics for breast cancer, we're all familiar with them. Breast cancer is the second leading cause for death in women across the globe, the statistics is 1 to 8, in some countries 1 to 7. To develop breast cancer, still the rate of breast cancer and the mortality can be decreased when you do early diagnosis. And this is why in most countries in the developing world we have screening, and screening is based on mammography and ultrasound and on tomosynthesis. And I think that in this domain, we are reaching the state where the machine and the algorithms are as good as humans and can support, for example, and I will show this, can support a second opinion to be done by a machine compared to another, like in London, for example, in London, in England, there is usually a second opinion in the usual process, and now you can have an algorithm replace one of the humans and one of the human doctors and support this process. And this is very exciting in my opinion. The challenge here is very big. It used to be very significant. So you have, this is just a list. I'm sure you can't read it, but this is part of the idea. This is how it is defined in the definitions for ultrasound and mammography in the atlas for radiologists. These are the different views. And actually, the task of a radiologist is to separate when a patient comes with a screening of a mammogram, is to separate the different to 5 different levels, or 0, 1, 2, 3, 4, 5, and also 6, and according to the probability of having cancer in this exam. And the performance across the world in the United States is not so high, okay? So the sensitivity, the average sensitivity is 86.9, and the average specificity is 88.9. It means that if we bring a machine to some places in the world where the clinicians perform less than average, then we can contribute to the process, okay? Then we have a machine that can actually be valuable. But also, it will be shown that in experiments and the products that are available today, the performance actually exceeds the level of the average radiologist. Now, one of the difficulties in breast cancer, actually I'm happy to say, is that the prevalence is extremely low, okay? If you have pneumothorax in 1%, for mammography, it's 0.5% of the population. And it makes it actually very difficult because to get a positive data set, it's extremely difficult. So this is the mapping of the situation that we have for this type of approach in the world. I think it's almost updated today, but you can see that the number of data sets and positive exams are huge, okay? You have to get about 200K exams, and you want to have thousands of cancer images, and you want to have them tagged, okay? You want to have them, some of the papers coming out of Korea, for example, and the companies in Korea, which is Lunit, actually tags thousands and thousands of images. And when we compare all of these approaches across time, it turns out that the volume of the data is extremely important. It's pretty obvious, but when you compare it, and when they compare it in a study to the diversity of the vendors and or the patient populations, actually the volume is even more important than that. Okay, so to reach this level of accuracy that we want to get, okay, today to get an FDA approved for such a product, you have to demonstrate performance of above 0.95 usually, and to get this performance, and you see here the Korean performance, it actually requires a huge amount of data, okay? They had 60K cancer images and almost 20K, so approximately 200K exams, and they had a significant amount of annotation in order to get this. Now, just to explain what we had to go through in order to get to this place, at the time, the idea was that we would try to match the radiologists. But here you can see the disagreement between radiologists. So this confusion matrix shows that some radiologists that had put 3 for a BI-RAD actually matched on the second reading of a BI-RAD 1. And the other part of the red square is the opposite. So we neglected this type of approach eventually and compared ourselves to biopsies, which we have for mammography. So this was a turnaround that enabled, I think, the companies to overcome this disagreement between radiologists and develop more consistent type of approaches that can actually predict what the biopsy eventually outcomed. So as I said, it seems, so if you read the recent paper, it seems that combining a first reader with a machine leads to better results than two human annotators. And that's in a paper by Salim et al., which was out in 2020. And I think that in the domain of breast cancer, we're getting there. But there are many other domains are still not there, okay? So going back to my experience at Zebra, I'm happy to share some of the stories that we have developed there. And I think one nice application is of incidental findings. Okay, so a person comes, has a CT because of a liver issue or liver condition, and on the way you detect a vertebral bone fracture, which is critical because it is usually underreported, okay? Only 30% global average reporting rate for these type of conditions. And if you are aware of it, you can avoid the really significant fractures that come out later. The mortality is from osteoporosis is very significant. And this type of application, you actually want to imitate what a radiologist or a clinician would do is to measure and identify the fractures that you can see the mild fractures, moderate fractures, and severe fractures, and this can increase the patients treated for osteoporosis and prevent morbidity and mortality with hip fractures. And we actually have such a product in Nanox, which is working, and there's a Nature paper based on this, and a huge clinical study going along in England with the NHS, and actually this is proven to identify these fracture, and as we said, this is a great outcome. Another incidental finding that you want to look into and is interesting and actually did not require such a huge data set is identifying coronary artery calcium, which is a pipeline. And usually a solution like this will be a pipeline, okay? You have the non-gated, non-contrast images, CT images coming in. First, you want to localize. You have this huge volume. You don't want to work on the huge volume. You want to crop the region that you're interested in. Then you want, in this case, you do calcium segmentation, and you provide a score which needs to match the score that is given by the clinicians. And this is a really good product also that is out there and available, and Nanox is selling. An important thing, I think I lost you. Okay. An important thing that I think people coming out of academia are not aware of, and I found it extremely important in my work in industry, is really building an infrastructure. So when you do your experiment, the process is always the same. You have the data, you have the labels, you build a training set, you train your model, you try all kinds of architectures, you'll try a baseline, sorry about that, and you eventually do some inference, and you have output and a validation. And then you ask yourself, is this algorithm good enough? Is it good compared to the state of the art in literature? Is it good compared to other products? Is it good compared to my baseline model? And then if it's okay, it's good enough, you can deploy it. And of course, this is a whole cycle of itself. But if not, you have to go back to your data, back to your labeling. You have to really smartly select the data that you want to annotate or you want to add to your model. And then you want to have, and then you need some annotating system. And then you want to train again. And this process in industry If it is not automated, I mean fully automated, it can take so much time and so much energy. And some of the things, the nice things that have been coming up these last couple of years is MLOps. So I really encourage people working in this domain to look into this and make sure that you automate as much as you can, because it's a very extensive amount of work. It's currently the work of data scientists or data analysts, but you want to select the data that will improve your algorithm. It's like us humans, or like having a child. You want to teach him something. He fails on something in school, a specific type of category of examples. You want to bring more example of that case and train him on that. So you want to automatically select them. And then you want to automatically tag them, because annotation is expensive. And you want to have the cycle actually working without a data scientist, so we can go to the beach and do other stuff. So really, this automation is really worthwhile, and there are actually many companies that are developing these automatic processes. Another important thing that we talked about is annotation. So it's inefficient to actually annotate manually. So of course, Tesla, Mobileye, as I said, Zebra, Nanox, we limit the amount of annotation that we do manually. We do manual annotation, unfortunately, but we limit it. And it's important to have smart processes to do this automation. So there are algorithms today that are self-supervised, that are semi-supervised, that are weakly supervised. All of these different categories are different. I can say a word about each one of them, but when you have a fully supervised, then you have everything annotated. You have the boxes for the finding in the slice, where you expect them. When you have semi-supervised data, you have only part of the data annotated, but all the rest is not annotated. And you're going to learn on a small data set and increase your performance as you go on the unannotated data set. And if you have, this is for semi-supervised, if you have weakly supervised, then you have the case that I said before. You're going to have these reports that are obtained from multiple volumes, and you're going to try to learn the exact location based on this weak annotation, which is not strong annotation. And there are also approaches today for self-supervision, which are extremely valuable, and I really encourage to look into them and apply them. And of course, when you eventually need to tag manually, do it smartly. Train your taggers, do quality control on them. There are many, many issues, lessons learned from all these processes, that you send the data somewhere, it's get tags, you get all this noise back, and then you need to reiterate, and this is time, and time is money, and of course it's very disappointing. So I'm going to skip this. And I think I'm going to sum up and open up for questions if you have. So I think I said a few things. I think I said that validation in the real clinical workflow is extremely critical, okay? So not everyone is aware of it. It takes time for companies to reach the field, to actually try their product, but it's really important to do this agile process of developing, going to the field, getting the conclusions back, and not working in the lab too long. It's important to scale up with multimodalities. Get your tags from text, from NLP, from EMR, from electronic healthcare records, and use several modalities to support one another. It's important. The volume of the data is extremely important. I really think that the fact that healthcare is still behind, and it is still behind compared to other domains, is the data. We need to make sure that we train on large data sets. The days of papers, like I did in my PhD, of 50 samples of MRI volumes have ended, in my opinion. So you can do that in some cases for some disease, for proof of concept. But if you really want something to work, Eventually, I think in most cases, you'll need a large data set. As large as you can get it, of course. And sometimes, actually, to be optimistic, we have been able to develop on small data sets for some problems. But it's really the data matters. I think additionally, I mentioned that there are domains that we are getting to be very good with AI. So AI, augmentation of the radiologists in the field of breast screening, as the paper that I cited said, the time has come. Infrastructure is extremely important. Annotation is an issue, and it's important to put time into weak supervision, self-supervision, all these state-of-the-art approaches. And of course, it's always important to dedicate your time and energy to the clinical need understanding and to make sure that you're bringing genuine impact to healthcare. And finally, I want to show you like this image. When I started my career, this was the upper image was from the labeled faces in the wild. It used to be a challenge to identify faces in the wild. It used to be a challenge to identify, detect, and today it's a non-issue, okay? Today the performance of machines in this domain is better. I don't think it will be so easy in healthcare, and I don't think we will be able to get there in all the healthcare domains, but in some of them we will, and I think it will bring a significant impact, so it's worth our efforts. And that's it, so thank you very much.